Now get ready to explore motorcycle optimization with our next presentation. Ciro Crivillaro, software engineer from Stretto and Carena, official UNIME MOTOSTUDENT team, will unveil the team's research on learning-based intelligent vehicle information analysis. Discover how deep reinforcement learning revolutionizes the setup of competitive motorbikes, leveraging advanced machine learning algorithms to maximize on-track performance.
Good morning. Today I want to show a new software was developed on the last year by the Stretto and Carena teams, and this software is Livia, learning-based intelligent vehicle information analysis. At the start, I want to start with a little introduction for the team. Stretto and Carena is a team of the University of Messina that's participated for 2 years of the MOTOSTUDENT team for the category petrols. And during these 2 editions was created 2 models and 2 bikes in 2020 and 2023. And during the last edition of the competition was developed a new software, obviously Livia in this case, because the idea of this software is to use the new technology of the neural network, in this case the reinforcement learning algorithm, where the most important parameters of this algorithm are agent, actions, environment, reward state. So in particular, in our case, the agent is the brain of the algorithm, so it's a neural network algorithm. We have an MLP architecture, multi-layer perception. For the environment, there are all possible tracks in exams. So well-known tracks like Largo circuits, Vallelunga, or as already mentioned, we can create custom tracks. And for the reward is the parameters to represent the performance of the vehicles. The state is the setup of the vehicles, and the action are possible changes to update the configuration of the vehicles. For example, increase the stiffness for the front suspensions, or decrease the stiffness for rear suspension, and so on. The idea of this kind of algorithm is similar to teach a dog to do the good actions. So the agents make decisions by the actions and send to the environment. The environment run the simulation, the dynamic simulation with the new setup. And the environment, after the simulation, send toward to the agent the reward at the future state. So the agent, based on the reward and the future state, do a new action. So this process until converts to an optimal setup or is the end of the training phase. For more details, if you want to go inside for any aspect, the agent is an NN architecture, so a neural network architecture. So make decision by interacting with the tracks in exams and receive the feedback, so the reward or a penalty, depends of the function of the reward we want to represent. The complexity of the architecture of the neural network depends with how many parameters we want to represent for the setup. So, for example, we want to represent just 4 parameters for the setup. The input layer, we has just 5 neurons, 4 for the setups and one for the reward. And the output layer depends how many actions we want to do to change the setup of the vehicles. For example, we have 3 actions: increase the suspension stiffness, decrease the suspension stiffness, and change gear radio, for example. We have just 3 neurons of the output layer. The hidden layer depends on the complexity of the problem, so we can, the default, we can choose 2 hidden layers. And for in this case, we have a complexity of the neural network with 4 layers. For the reward, in our case, the simulations, in particular, is composed with 2 parts. So take the action for the agents and provide to the reward, send the reward to the agents. It's composed in 2 parts. The real environment is the first part, to take actions for the agents and change the state for the setup of the vehicles, run the simulation by real times, and get the results from V-grades, elaborate the results, and send the reward at the future state. For the reward is important parameters that represents the performance, in this case for the vehicles, and we represent with the reward with this function, object is minus penalty crash, where the objects could be lap times attacks, average lap time, or performance chance. On the right side, we have an example of the configuration in a lap time attack. We have three condition when where t is the iterations. Each time found a lap time, we check if the lap time is the new best lap time or is less the best. For example, in the second condition, when found a lap time is equal to best, it could be or the new lap time, or the new best lap time, or the same best lap time with a new setup, or a new setup. So we consider the 2 solutions for the setup. And the last one, when we found a new setup that leads a new best lap time. For the state, we divided in 2 parts. Is the current condition where the vehicles and environments operating. In particular, for it's divided in 2 parts. So the static states and the dynamic states. For the static states are all presetted value that you can set before the execution of the training phase. And could be, for example, the water temperature, road surface condition, or the characterization of the tracks in exams in the various sectors. And the dynamic states are all possible parameters that we want to change during the execution. So in our case, it's the setup of the vehicles. So change during the normal execution of the neural network. And here we can the suspension stiffness, the gear ratio, and so on. And for the action are a set operating. We wanted to do to improve the performance, but also to lead a bad setup, because sometimes during the training phase, the error algorithm. In the first part of the training phase, the algorithm can do the action to lead unstable vehicles. So in this case, we have the penalty for this reason. And there are increasement to the stiffness of the front suspension, decrease the stiffness for rear suspension, gear ratio. So it's all possible operation we want to do to improve the performance of the vehicle, so I changed the setup, in this case, of the vehicles. For the state of arts, was analyzed on parts of the real complexity problem, with just 4 parameters for the setup, for the front suspension, the rear suspensions, was evaluated around 6,000 laps for the trainings, and the environment was used Argo circuit under standard condition. So sunny for water condition, good surface condition. And for the mathematical model of the vehicle was used our mathematical model elaborated for the dynamic teams. And the results. Okay, in this case, we have how the neural network works. We have these metrics are the representation of the state, and the green dots are the good action to do in these situations. Depends of the state. On the left side, we have initial state and the action we want to do. But it's randomically, so the initialization of the state and the action to do is randomically. After some iterations, at the end of the training phase, we have that the action, for example, the action 0, is compact to a region. So in these parts, the good action to do is the 0. And if we have in the state the right part of the state, the good solution to do, the good action to do is the action 2. Okay. For the lap time, on the left side we have the trends of the lap time. Was removed the first part of the simulations because it's the part when the motor fault. So it's not necessary to show in order to show the trends of the lap time. We have at the beginning a high value of the lap time. After some episodes, each episode, the number of laps for each episode depends of the conversations. We have a conversation to the for RL algorithm optimal lap time. On the right side, we have the trends of the rewards. So we have at the beginning a high negative value caused due to the penalty. So minus 1,000 is the penalty crash. So at the beginning we have a high number of penalty crash, but after some iteration we have a rank increment of the reward that tend to 0. That is when found the same setup or new setup for the best lap time. For the validation, to validate the results of neural network algorithm in general, the first phase of the validation is to analyze the learning curve of the algorithm, in particular the loss and validation loss, in order to find the case we have an overfitting or underfitting, or if the model generalizes well the dataset. And the second phase was analyzed the setup with the dynamic themes. So the setup resulted by the iteration of the neural networks. And the third simulation, the third validation is analyze the simulation telemetry by real time, and finally comparing the result with the real lap. For future developments, this is the basic idea for this kind of solutions. For future developments, the first part is to integrate this kind of solution in data acquisition systems in order to adapting the neural network directly on the driving styles, and or increase the complexity of the model. So it was analyzed just on a subpart of the real complexity problem with just 4 parameters, and we want to add more parameters to improve the accuracy of the decision making of the neural networks. And was created also a lineup to the future project around these based solutions, and we creating a new spin-off to support this project. In particular, until 2024, the integration was mentioned before it. Until 2025, We want to create a smart suite in order to find the driving styles of the driver and the cinematics, the characterization of the cinematic driver, and connect to Livia in order to adapting the decision based on the driver, and finally integrating all systems in a single suite in order to improve the decision making, to improve the performance, or to change the setup depends of the driver. Thank you.
Thank you very much.